for a little bit of feedback. All right, and Andrew, definitely your calculus education is far more important to me than whether Keelan Williams emails me. Steven, if you could start filming.
I have.
You have. Okay, fine. Be that way. All right, so problems 1 through 6, 9 through 12. Here's what I'm going to offer. If these did not go well and you need to make corrections tonight and turn them into me tomorrow, that's fine. But let's see how well we did first. All right, here's the thing. Almost all of these problems, almost all, involve L'Hopital's rule. How do you know you're going to use L'Hopital's rule? What do you have to look for first? Before you do anything at all, David? Oh my gosh. Careful, there's a hole there.
Indeterminate form 0 over 0 or infinity over.
Okay, if you get one of the indeterminate forms, that is assigned to you. L'Hopital's rule is the way to go. And there was even a little note here at the top that says, hey, be careful, not all these problems involve L'Hopital's rule. For example, number
1.
2.
Oh. Yeah.
2. All right. Now, I had a couple of conversations yesterday. Folks were like, Coach, I don't get it. They look the same. Why would you do that? Because they're not the same. So problem number 1, if you try evaluating right away, you get 0 over 0, indeterminate form. This is a sign. Use L'Hopital. When you use L'Hopital, I better see that little limit as x approaches 0. You take a derivative, not the quotient rule, L'Hopital's rule, and you're going to get 0 as your final answer. Is everybody okay with this one? Okay, number 2, however, when you try evaluating at 0, you're going to get 4 over 0, which is not one of the indeterminate forms. It's just not. What happens if the numerator gets close to 4 and the denominator gets close to 0? If the numerator is getting close to 4 and the denominator is getting close to 0, then the whole limit is approaching infinity. So you would say the best answer here is limit does not exist by unbounded behavior. All right, number 3, definitely L'Hopital. Derivative in the top, derivative in the bottom, don't forget your chain rule, 2/3. Okay, number 4, definitely L'Hopital, 0 over 0 again. You need to remember that the derivative of tangent of 2x is secant squared of 2x. And the derivative of tangent of 3x is secant squared 3x times 3. Do a little bit of stuff here. I can never evaluate secant or cosecant or cotangent directly. I always have to say secant squared is like, oh, secant squared of 2x times 2 is the same as 2 over cosine squared of 2x. In my old man brain, I cannot work directly with secant. I always switch it to the reciprocal of cosine. And then I evaluate and get 2/3. Celeste?
Couldn't you also write, at the beginning, write tangent equals 2x over 3x instead of...
Tangent equals 2x.
I mean tangent of 2x over 3x.
Oh gosh, no, that would be so bad because there you would be using your confidence that I wrote about to make up rules that actually don't work. It is not true that the tangent of 2x divided by tangent of 3x is the tangent of 2x over 3x. Not true. Not true. All right, for friends, how do we do on 1 through 4? Mostly doing okay? Aaron, you okay? All right, I know you get caught up with us. All right, number 5, indeterminate form, but now it's the infinity times 0 indeterminate form. Infinity times 0, somebody has to move to the denominator. Somebody's got to go. It might as well be the x that you're multiplying by so that now you're dividing by 1 over x. Derivative in the top, derivative in the bottom, the negative 1 over x squareds cancel out. Not too bad, we're going to get 1. All right, number 6. Oh, number 6. Oh, number 6. Do I love me number 6. Number 6, limit as x approaches infinity, natural log of x, the whole thing cubed over x, infinity over infinity. I have to see that you're checking the indeterminate form piece. Everybody okay? Take a derivative. Derivative in the top, 3 natural log of x, the whole thing squared, times 1 over x. Derivative in the bottom is 1. And you might think, hey, that's great, wonderful. Well, no, if you actually rewrite it, 3 natural log of x, the whole thing squared over x, which is infinity over infinity. Guess what? You gotta do it again. So now this next time you use L'Hopital, you're gonna get 6 times natural log of x times 1 over x over 1, which is 6 natural log of x over x. Oh, indeterminate form again. Hopefully not too bad though. Take one more derivative. You're going to get 6 over x. Final answer is 0. Everybody good? Okay. Number 9, things start to get a little bit crazier, but not horrible. Okay, if I'm approaching 2 from the right, denominator here is 0, denominator here is 0, I'm getting an infinity minus infinity. The way that we handle that, hopefully this was kind of obvious. Common denominator. Okay. So if you get a common denominator, once you do that, everything kind of just becomes easy, and it should be negative 3 over 2. But the key is getting a common denominator so you can get into that 0 over 0 or infinity over infinity form. All right, number 10, another one. If I see I'm doing subtraction here, I'm going to get infinity minus infinity again. Get a common denominator. My common denominator, I think x minus 4 would work. You're going to multiply top and bottom, and if all goes well, you're going to get 1 over 4. Number 11, take the limit as x approaches infinity of x to the 1 over x. You're going to get infinity to the 0, which is clearly an indeterminate form, and it's one of the ugly ones. This is like really one of the ugly ones. You're going to have to do that thing we did yesterday where you say, let y equal this, and then your natural log properties, and you do your little switcheroo. You take one derivative, you're going to get 0. Be careful, 0 is not the answer. 0 is what the natural log of y is equal to, and when you're done, you should be getting 1 as your limit. And you guys honestly got 1 as the limit. 2 people and a lot of sad-looking teenagers. 3 people and sad-looking green gnomes. Okay. All right, and number 12. Ooh, look at all that beautiful work. X over x plus 1 to the x power is going to get you 1 over infinity. You're going to do your little trick again. Y equals your limit. Take the natural log. Do your little switchy here so you can bring the power down in front. Take a derivative. I think on this one you had to use L'Hopital's rule twice, maybe. Final answer should be 1 over e, or e to the negative 1 power. Okay, if this went well and you're like, I am proud of this work, please put that in the middle of the table. I will pick that up, I will grade it, I'll give you some feedback, and you'll get this back tomorrow. If you need to hold on to this so that you can make some corrections tonight, keep in mind, for all the people that are nodding along with me, this is in addition to the work you're going to get from me tonight that's due tomorrow, regardless of your work schedule, regardless of how sad the email is that you sent to me. Not you, Polymon. Polymon sent a sad email. That's fine. Everybody good? All right, so let's get this homework assignment in the middle of the table, please. Let's also get those of you that made test corrections and reflections, but you forget to have mom or dad sign it. You could put that in the middle of the table. Also, I've got one more thing that I need to pass back to you all. This is the first assignment on L'Hopital. Aaron. Eile, can you tell me what your score is on that? Giselle, if you can tell me what the score is on that. Okay, somebody did really well. Unfortunately, I have no idea who this is. David, I need you to put a score on that. I'm going to put it on my desk. Andrew. Andrew sits over here in the captain's chair.
Steven.
Okay, nothing from him. Lewis. Here you go.
Oh, yeah.
Carmen, there you go. Celeste, there you go. Myra, if you can give me your score and put it on my desk. Polymon, score and put it on my desk. Aaron, put a score on it, put it on my desk. And I don't mean a random score, like I'd like 114, please. I mean, how many did you get right out of 12? Okay, just put 10 out of 12. No need to even reduce that. Yep. Or you know, with all of you that needed to write the score, you can just put it in the middle of the table and Carmen will come around and take care of it. It's negative.
You don't want that.
But that's actually not the score that's going to go in my grade book. I was going to put in an 88, but if you like an 85, okay, I'm going to do what I got to do.
Pick everyone's or just
Only the people that you like. I think everybody has some stuff they're turning into me, either the score and the assignment that I just passed back, or the corrections that were due yesterday, or the homework assignment. If you're not turning in the homework assignment to me today, you're turning this in to me tomorrow, because you want to make corrections to this.
very clear.
Oh yeah. Is everybody okay? Are we at that time of the year where it's like rough to be a senior?
Oh yeah, maybe.
Does it get loaded?
Yeah. Yeah, sorry. As the most senior of the seniors in the room right now, right? Senior, but in a different way. Thank you, you little green gnome.
Is he writing your letter of rec?
No, I'm not writing a letter of recommendation. What I would say though is it does get harder.
And no, we have not reached that.
I'm not saying that to bust the bubbles, but yesterday I was worried about you all. Today I'm worried about you all.
Tomorrow can be
Nah, tomorrow I'm gonna stop caring. I'm wondering if it's calculus stuff, if it's other things.
College stuff.
College stuff.
Have you ever tried to get into a college?
No! I skipped that part. I just went from high school to like teacher.
Also, like you're like the Kobe of math.
Exactly, whoever he is.
Oh,
I know Kobe.
I was like,
Not personally, but I know who we're talking about.
He was one of the students.
Yes, I came out with a master's degree. Some people get a birth certificate. I had a master's degree. All right. Everybody doing okay? Giselle, you okay? All right. All right. So I need everybody to get a separate piece of paper and a ruler, and I need to take attendance. All right. I'm gonna do this job. I've got a new theorem coming your way.
I'm used to this.
well, that is. You alright? That's not. Also, I'm not aware.
Alright, so here's what I need you to do. I need you to draw a continuous function. Any continuous function. Even if it is not a function whose name you know. It doesn't have to be a parent function. It just has to be a continuous function. So for example, I don't know. There's my continuous function. Don't draw mine, draw your own.
The whole paper?
Huh?
The whole paper?
No, not the whole paper. You're going to draw a couple of these. So,
why we need to root it?
because there's the next step. God. So, for this continuous function, I want you to look at this continuous function on a restricted domain, on a closed interval. So pick a starting point and pick an ending point. Anywhere on the function is fine, but draw a continuous function, draw a starting point, draw an ending point, and what I want you to do is connect those 2 points with a secant line. You guys know what a secant line is?
I can't do that with this.
Yes, you can.
Polymorph.
That's okay. There's nothing wrong with what Polymon's doing right now. We've got a continuous function, we've got a closed interval, And we've got a secant line connecting these 2 points. Maybe your graph looks something like this. You're like, here's my starting point, here's my ending point down here, and if I'm going to connect those with a secant line, well, you guys know what a secant line looks like. My question for you all is, if you were on your graph to connect these 2 points with a secant line, here's my secant line, is there a place inside this interval where there's a tangent line with the same slope? See if you can find one. Is there a place inside this interval where the tangent line has the same slope as the secant line? If so, draw it.
I'm gonna take my post-it note back.
Yes. What?
No, wait.
Okay, so this is the flat. So then here? Right? Okay, okay. So then, okay.
All right. So David, we got Ilay. How many of y'all have found a place where the tangent line has the same slope as the secant line? David's found one. Palamon's found a whole bunch. Work in progress. Anybody find more than one place? Me. More than one place where this happens.
Oh, me.
Okay, let's see. So for my graph, if the blue represents the secant line, my tangent line, maybe I want to envision just sliding this up. Is everybody okay that, like, here, my tangent line has the same slope? Okay, is that it? That's the only one?
No, you can go down.
I could also slide it down, and so I'm going to get another one where the tangent line has the same slope as the secant line. Everybody okay? Approximately the same slope. Okay. Did anyone find a situation where this doesn't happen? Or does it always happen? Did anybody draw a function? You picked your endpoint, you made a secant line, and there is no place where the tangent line has the same slope. God bless. Oh, yours looks so much like mine. Let me take yours. I want to take yours. All right. So Celeste drew this one over here, and she picked this beautiful function. Her endpoints happen to be here. Kind of looks to me like your secant line is horizontal. Horizontal tangent line, those are good. Happened twice. Halimon, always a creative individual here, starts off with a line. Now my instructions were start with a continuous function. Is that continuous?
Yes.
Sure. Okay. And then he picks 2 points. And then he makes a secant line. And what's the problem that we're running into here? Or
The secant line equals the first.
the secant line is the same as the function, right? And so here's my secant line. Does anybody see a place where the tangent line has the same slope?
Yes.
Like here, 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 here. All the freaking places. Okay, I'm coming. Did anybody find a function where this wasn't true? Did anybody find a counterexample? Okay, we've got 11 really smart people, 12 with me, bunches on the other end of the camera. Nobody found a counterexample? If no one found a counterexample, then you might say, oh, then it's going to be true all the time that for a continuous function, if I connect the endpoints, find my secant line, I'm always going to have a tangent line, a place where the tangent line is the same. There is a counterexample, and I want you to find it. I'm looking for a continuous function. You're going to pick the endpoints. You're going to find the secant line, and there will be no place where the tangent line has the same slope. Don't talk to me, talk to friends. I need to talk to Kia. Okay.
Wait, yeah, but this is,
Yeah.
Oh, yeah, okay.
All right. Anybody find a counterexample? Exponential. I need to see it. I need to see it. If you have a counterexample, I want to see this counterexample.
We tried.
You tried an exponential, and it seems to be working.
Yeah.
There is a counterexample. There is an important counterexample that I'm hoping someone's going to come across. There is a function that you can draw. There are endpoints that you can pick. And when you find the secant line, there is no tangent line that has that same slope. And a couple of people mentioned it earlier, but no one's drawing it.
Oh, that's the value.
Why are you surprised?
I'm looking for a counterexample.
No, I was sure.
And then you get.
No, you were like, why does it not be?
What about it?
Because it's not people. Yeah.
Or you can pick two.
If we graph the absolute value function,
If you pick.
where would you pick the endpoints so that you have a secant line, but you have no tangent line with the same slope? One,
How about you?
maybe two. What if I picked this as my interval?
Okay, yes.
What if I pick that? What happens? Imagine you're on a secant line. You get your secant line going on there. Where would we look for a tangent line to have the same slope? At the cusp point? So the problem is, for the absolute value graph, you guys know the slope over here is always going to be 1. And that the slope over here is always going to be -1. And this blue line does not actually seem to have the same slope as either of these two, right? And so you might say, oh, but how about at the cusp point? Can I draw a tangent line there that's going to be parallel to the secant line? Why not, Aaron? What do you know about the tangent line at the cusp point? It doesn't exist. The slope here does not exist because of the cusp point. So if that's true, this is a really good counterexample that I want you to keep in mind. This function and other functions like this do not satisfy this condition. I think pretty much all the functions you guys picked out, they all had to be continuous to begin with, and everybody drew a smooth curve. We have another word for smooth. It's been a while since we've used it.
Monotone.
What?
Monotone.
No.
Monotone, no.
Oh, okay.
There's another word that we have in the calculus for smooth. If the derivative exists everywhere, you would call it differentiable. And so this gets us into the mean value theorem. So let's talk about the mean value theorem. The mean value theorem is one of those that it may not be as intuitive as you would like, but stay with me, we're going to get there. And darn it, I thought I had removed this graph, but apparently I did not. All right, so here's what the mean value theorem says. The mean value theorem says that if a function is continuous, you guys know what that means, right? No holes. What else? No jumps, no breaks, no vertical asymptote. So if you have a function that's continuous on a closed interval AB and differentiable, differentiable just means differentiable means first you have continuity and you have something more. The something more is that the derivative exists. If you have a function that is continuous on the closed interval and differentiable on the open interval, so we've got a function like this one. We are continuous, no holes, no jumps, no breaks. We are differentiable in that the curve is smooth, there's no cusp points, no vertical tangent lines. Then here's what the mean value theorem says. Mean value theorem says if you calculate f of b minus f of a over b minus a, you guys know what that is? F of b minus f of a over b minus a, what is that? This is slope, be specific. Slope of what? F of b minus f of a over b minus a. This is slope of secant line. That's this guy here. What the mean value theorem says is there is always a place where f prime of c is slope, but this is like slope of tangent. There's going to be a place always inside the interval where the slope of the tangent line equals the slope of the secant line. This is what the mean value theorem promises us. But the function has to be two things. Continuous and differentiable. Okay, so stay with me on this. So the mean value theorem says that if a function is continuous on a closed interval, like bear clause, like think about like closed interval, right? A closed, not claused interval, like bear clause, right? I'm thinking like on a closed interval, and differentiable, which means smooth on the open interval. So like I want to be really clear. There will come a time where you're going to appreciate that I did this. Differentiable on the open interval, like parentheses. Then there's always a place inside the interval where the slope of the tangent line is equal to the slope of the secant line. Are we okay? This is exactly what we did in that initial exploration that maybe didn't go as well as I was hoping it was going to. Okay? But the thing is that C is inside the interval. So it has to be true that A is less than C is less than B. This means C is inside the interval. The mean value theorem doesn't necessarily tell you where that special point is. It just says that it does exist. So in this case, the black is my secant line. Where do I have a tangent line that has the same slope as the secant line? Like right up here. So f prime of c tells me like tangent, but the c value that I want is down here. X equals c is between a and b. This is the big thing with the mean value theorem. Continuous on a closed interval, differentiable on an open interval. There will always be a place inside the interval where the slope of the tangent is equal to the slope of the secant. Tell somebody near you, make sure they've got this under control. Alright, let's try this. Alright, for those of you that like checklists and processes, there's one at the top of the next page that takes you through all the steps of what you're going to do. We're going to do two relatively quick model problems, and then you guys are going to get some time to practice. Here's what the problems are going to sound like. For the function f of x equals 5x minus 4 over x on the interval -4, -1, find the value of c guaranteed by the mean value theorem, or tell me why the mean value theorem cannot be applied. So, if the mean value theorem can be applied, I have to check two things. First thing I have to check, continuity. Second thing I have to check, differentiability. Okay, so first of all, let's check continuity. Is f of x continuous? Yes or no? I deliberately picked a function that's not a parent function. You may not know exactly what this graph looks like. Is this function continuous? I'm hearing a couple people saying yes. A whole lot of folks not responding. So I think there's a lot of folks that aren't really sure. Is there a place where this function might not be continuous? If so, where would you look? Don't overthink this. Where would this function not be continuous? F of x equals 5x minus 4 over x. There's a problem area. Lewis, where's the problem area?
It would be 0, but it's not in the...
Okay, I know f of x is not continuous at x equals 0 because that would put a 0 in the denominator. Are there any other places? Any other places where this function won't be continuous, or is that it? Right, I only have one problem area in my denominator. I only have like one candidate for a vertical asymptote or whatever. So not continuous at x equals 0, but is continuous everywhere else. So, can I use the mean value theorem? In order to use the mean value theorem, I need my function to be continuous on the closed interval -4, -1. If I'm just interested from -4 to -1, am I continuous?
Yes.
Yeah, because my one problem area is not in that interval. So I'd say something like, therefore, continuous on the interval -4, -1. Not ready to use the mean value theorem, though. You've only checked one condition. The other condition that you have to check, you have to check differentiable. Differentiable just means, does the derivative exist? Does f prime exist? Well, let's see. Does that derivative exist? F prime is low, d high, minus high, d low, low, low. If I clean the numerator up a little bit, I'm going to get 5x minus 5x plus 4 over x squared, which is 4 over x squared. Does the derivative exist? Is the derivative always going to give you a number?
Well, not at x equals 0.
The derivative has a problem, which shouldn't be a surprise because the function wasn't continuous at x equals 0. Your derivative can't exist at x equals 0 if the function doesn't exist at x equals 0. So I would say, though, does this guy exist?
Yes.
4 over x squared? Yeah, I'm going to get numbers out of this except at x equals 0. So I would say f prime exists except at x equals 0. Therefore, f is differentiable on the, here's where you need to be careful, on the open interval -4, -1 is all that I care about. I've got my continuity condition. I've got my differentiability condition. Can I use the mean value theorem?
Yes.
Yes, all that we've done, therefore the MVT applies on the interval -4, -1. This is not the end of the problem. Don't get confused and think I'm telling you that you're done. All that you've done with all of this work, you checked continuity, you checked differentiability, you've told me the mean value theorem applies. Now the question is, what's the value for C? Well, what's so special about the value for C is I need to first find slope of secant line. So f of 4 minus f of -1 over 4 minus negative 1, slope of secant. Well, f of 4, I'm going to plug in 4. 5 times 4 is 20, minus 4 is what, 16? Divided by 4 is that 4? Aaron, what's that? Oh! Oh, so awkward. Thank you for catching that. Slope of secant f of negative 1 minus f of negative 4 over negative 1 minus negative 4. Thank you, Aaron. Okay. So find f of negative 1. Plug in negative 1. 5 times negative 1 is negative 5, minus 4 is negative 9, divided by negative 1, I think, was it 9? Minus f of negative 4. Negative 20, negative 24 divided by negative 4 is 6. Negative 1 minus negative 4 is 3. 9 minus 6 is 3. Slope of my secant line is 1. Everybody okay? Okay. This is not what I'm looking for. This is the slope of the secant line. What I need, where is the place where the derivative is equal to 1? Right. What I need is I need my derivative. Well, good news, we already know what the derivative is. I need the derivative to be equal to 1. Okay, and so if I solve this equation, maybe you want to multiply both sides by x squared. You're going to get 4 is equal to x squared. If 4 is equal to x squared, what's x? X equals 2.
Or negative.
Or negative 2.
Has to be negative
So I'm curious, how many solutions are?
1.
Oh, no one fell for it. No, everyone's like, 1. Somewhere, someone is going to be watching this video, and they're going to be thinking 2 solutions. Why? Why, David? Why?
Because of the interval. They gave us an interval that means equals -1.
Right, the mean value theorem promises you a place inside the interval. I really want to emphasize the insideness here. X equals 2 is not the solution. X equals negative 2 is the solution. Everybody good? We get this under control? I'm going to leave this guy up here as a beautiful model. See what you can do with problem number 2. We'll talk in a minute.
Negative 1.
What?
Anybody done yet?
Yes.
Okay, good. Palamon, why are you done so fast?
Because it's not continuous.
I'm sorry, what?
F of x is not continuous.
F of x is not continuous where?
At x equals -1.
At x equals -1, and that's different from this problem. Why?
Because to be able to use the mean theorems, you
Yeah.
have to.
The mean value theorem? Since f is not continuous at -1, guess what your conclusion is?
You can't apply it.
F of x is, but here's what I need to see. F of x is not continuous on -2 to 2. And the question asks, explain why you can't use the MVT or find the value of c guaranteed by the mean value theorem. F is not continuous at -1. F is not continuous on the interval. Therefore, MVT does not apply. Very good. All right, so there are some practice problems. I want you guys to see what you can do. I'm especially interested in number 1 and number 3.
Should you go like this?
Why would I do
Okay,
that?
go to the back. I'm just trying to help you out in life.
Don't worry, I'm good looking. It's okay. A little bit of sweat or a little bit of marker, that's just a job hazard. That's all right. So for the friends at North Central and East End, I'm going to silently work through this problem. What you might want to do is hit pause and come on back in a little bit. For all the friends that are in the room, I'm going to silently go through this problem so that they have something to look at. No, don't hit pause. They should hit pause. You should just keep working. Okay. So my first question is about continuity.
I think what you're saying is that you can have two divide that you can just say x. You can have like if it's 0, 0, 0. I think you're thinking about like,
Are we okay with this functions continue? Why is it continuous? It is. It's a polynomial. There's no denominators. You're not dividing all the things that would make you think, "Whoa, can't you know, I'm going to have some problem." None of those things are happening. We're good with continuity? Right, it's a polynomial. You're not dividing by anything. You don't have any vertical asymptotes. Continuity should be relatively quickly. Function is continuous. Okay, how do you know it's continuous? Well, yes, that's right. So it's continuous on because this is a polynomial. When I find the derivative, we found the derivative. Okay, the derivative is also a polynomial. That's going to be good too. So the MVT applies. Love it. So you find slope of secant line, and you go from there. And I don't know, but I love that.
2/3.
Oh no, I'm gonna write it out like this one. Don't you know? Just like
Yeah, 2/3 and 1.
because you plug in the derivative for that.
No, it's not correct.
Okay.
All right, so secant f1 minus f1 is 1 minus 1 is a -2, f of -1 is -1, minus 1 is -2, plus 2, I think that's 0 over 2. We're getting -1 for the slope of the secant line. That's your goal. And then you say, okay, f prime of x is 3x squared minus 2x minus 2. That's equal to -1. I'm going to add 1 to both sides. And I'm going to factor 3x and x minus 1 plus 1. I think if you actually do the factoring correctly, you get negative 1/3 and positive 1. No? How many solutions?
Yeah.
2? 1?
Wait, no, it's closed.
None?
It's closed.
No clue?
No, it's-
Okay, first of all, I have a feeling I lost some folks with the factoring. Everybody okay with the factoring? Right, I just didn't do the box, most of you guys are gonna do the box. Negative 1/3 and x equals 1 are your candidates. My question for you all is 1 solution, 2 solutions, or no solutions? Show me on your fingers, what do you think? 1 solution, 2 solutions, no solutions?
As opposed to-
2 solutions, 2 solutions, 2 solutions, 2 solutions, 2 solutions, 2 solutions. Go back and read the mean value theorem one more time. One more time. The mean value theorem like on the page before, Aaron. The statement of the mean value theorem tells you something very particular. Halimon, what's the thing?
It has to be inside, there's not a
Inside the interval, inside the interval. The reason that I'm not going to pick x equals 1, you're not inside the interval, you're at an end point. It has to be inside the interval. The one that you guys did before was a little more obvious. I needed one where the problem happens at the end point. We're not interested in end point, we're interested in interior stuff. Okay, for all the friends in the room and all the friends watching at home, we're okay? All right, try number 3. Yeah. You set the slope equal to the derivative of the function. Exactly. And then you solve the equation. You're factoring. Right, but here's the problem. You're doing your factoring. This is something you do when you have a problem with you don't want to add 2 to both sides, you want to add 1 to both sides to get 0 equals stuff and then factor it. You're good. All the friends right here, Lewis. Sure. Okay, right, but the graph of y equals x is continuous, sine of x is a continuous function. Okay, friends over here. Okay. Yes, practice problem number 3 is continuous. Number 3. Number 3, right, you don't have any denominators, you don't have any vertical asymptotes. She's just early. I have you guys for 1 more minute.
How would you say like, no.
Thank you for reading that for me. That's what I was thinking.
So if g of x is continuous,
Yeah.
okay, we know that it's obvious, but can we just say that?
I would be okay with, in this case, you would say. Because sinusoidal functions are known to be continuous functions. Polynomials are known to be continuous functions. And you're just subtracting 2 known continuous functions. If you had a denominator or you had some parent function that you know has problems, then I'd be much more cautious. All right, sadly it is 9:33 and the next show is coming in. Tonight's homework. And if you did not turn in last night's homework on locales, this is in addition to that. It's the assignment for lesson 52 in the problem set packet. Do not make the mistake of forgetting to read the instructions. Read the instructions. Lesson 52. Assignment, lesson 52. All right, friends, see you later.
I'm gonna get a sandwich.
You will?